Yeah, Shivaji, we are live. You can start.
So let me introduce the speaker. Our speaker today is Abhisekh Sankaran. Abhisekh is a postdoctoral research associate at the University of Cambridge, where he is working with Professor Anuj Dawar. And prior to this, he was a postdoctoral fellow at the Institute of Mathematical Sciences, Chennai. He completed his PhD and also his bachelor's and master's from IIT Bombay. His research interests lie in mathematical logic, particularly classical and finite model theory, and also in parameterized algorithms. Today, he will be talking about a classical model theoretic result in the context of finite structures. Over to you, Abhisekh.
Shivashish?
Yeah, Abhisekh, do you want to start?
Yes, sure.
Yeah, go ahead.
Yeah. There's a bit of an echo. I mean, there's a repetition of things, but okay. Nevertheless, thank you very much, Shivashish, for coordinating the arrangements for this talk. And thanks to Professor Sen for giving me this opportunity to talk about the work that I've been doing. And thanks to all of you for having come for the talk, and also the people who are watching the talk on live stream. So thanks for attending. Yeah, it feels great to be speaking here at TIFR. So of course, I have visited TIFR a number of times in the past during my PhD and even earlier. And in fact, I have even had faculty members from TIFR who are currently here. Professor Pandya was on my PhD panel. But I've never given a talk at TIFR, and so this is my first time. And it feels great to be here, and also great to be speaking on a very special date, which is quite palindromic, as you can see on this one on the slide. So I don't know, it will happen the next time only in 2080. So so thanks for giving me this opportunity to speak on this day. Okay, so what I intend to talk to you about today is a work that well, it's a relatively recent work that got published only last year at CSL. This is joint work with Anuj Dawar. And this is about looking at classical model theory, a particular classical model theoretic result in the context of finite structures. In particular, this result is about looking at the extension preservation theorem in the finite and looking at its connection with prefix classes of first order logic. With respect to background, I think if you just know the syntax and semantics of first order logic, I think that's more than sufficient for the purpose of this talk. And if you do not know the syntax and semantics of first order logic, I think that does not matter as well, because I think you should be able to get the gist of the ideas that are involved. So it is not any demanding on the background at all. If you have any questions at any point in time, please feel free to ask me, interrupt me, and I'll be very happy to take your questions. If there aren't any questions immediately, then I'd like to begin. Okay. Yeah. So the theorem that I'm going to talk to you about today is what is called the Watchtowers preservation theorem. To set the context for this, so extension preservation is a well-realized property in computer science. By extension preservation, I mean a property or a class of structures which has the property that if you take a structure from the class, you take a superstructure of that structure, and the superstructure is also in the class, which means the class is closed under taking superstructures. Yeah, in the context of graphs, superstructures means supergraph, which means that you are looking at a graph and you're looking at an extension of it, such that the original graph is an induced subgraph of the supergraph. Yeah. So we are looking at these supergraph closed classes of structures, and such extension preserved properties are plenty in computer science. For example, graphs containing a triangle. If a graph contains a triangle, certainly any supergraph also contains a triangle. Okay, graphs of chromatic number at least 6, graphs of vertex cover number at least 10, graphs of clique width at least 15. So all of these properties are extension preserved, and this is just a small sample of the number of properties that have this meta property. Now, it turns out that way back in the mid-50s, Watchtowers, two Polish logicians, proved a characterization of extension closed or extension preserved properties that are first order definable. Okay. So these are extension preserved properties of arbitrary structures that they're looking at. So in the context of graphs, it will be looking at finite and infinite graphs. And they're looking at extension preserved properties of such classes of structures that are first order definable, and they give a syntactic characterization for all such properties. Okay. In particular, they show that any such property is one that is definable using a very simple fragment of first order logic called the existential fragment. The existential fragment is a class of all those first order sentences which have this very simple syntactic form which just says exists, and then a quantifier free formula. Okay, like for example, exists x1, exists x2, exists x3, such that edge between x1, x2, edge between x2, x3, edge between x3, x1 says the presence of a triangle in the graph. Yeah. So this very simple syntactic fragment called the existential fragment, they show is expressively complete for the property of extension preservation over arbitrary structures, which means that any property that is extension preserved can be described using any property that is extension preserved and first order definable is also definable using this very simple syntactic fragment. Now, this particular theorem also relativizes to any class of arbitrary structures. So the theorem was first shown for the class of all graphs, all structures. Okay, and then they show that it is also true for any class of arbitrary structures that is itself definable using a set of first order sentences. Such classes are called elementary in model theory, and they show that this theorem relativizes to any class of elementary structures. Now, this theorem is historically very significant because it constituted the first applications of the compactness theorem of Kurt-Gödel. Okay, and it really opened up the area of preservation theorems in model theory. So on the basis of this theorem and its proof method, various other preservation properties were considered, like preservation under homomorphisms, preservation under surjective homomorphisms, preservation under substructures, under direct products, under reduced products, under unions of ascending chains, under intersections of descending chains, a whole lot of these, and then preservation theorems for all of these preservation properties were proven. In fact, preservation theorems were proven even for extensions of first order logic, like infinity logics. So this was a very active area of research from the mid-50s to the mid-70s. And it is through these investigations that the subject of model theory really grew. And now, of course, model theory is a very flourishing subject with a number of connections to mathematics and computer science. And the Watchtowers theorem is very significant in this historical development of the subject. Okay. Now, Watchtowers and computer science. If you can just allow me, there is a bit of noise coming there because of some construction going. Let me just close the window. If you can just give me a bit. Yeah, I think this should be better. All right. So Watchtowers and computer science. Well, what's the connection between the two? Well, there's plenty of connections. First of all, of course, it talks about extension preservation, which we already saw is quite well realized in computer science. But what about the theorem itself? What about this characterization? How does this help? So the Los-Tarski theorem is of much algorithmic and structural interest whenever it holds over a class C of graphs. More generally structures, but let us just look at graphs. First of all, you can show that it turns out that if you have a class C of graphs that satisfies Watchtowers theorem, which means that any extension closed subclass of the class, which is first order definable, is also definable over the class using an existential sentence. Okay. Then any such extension preserved FO defined subclass D of C is already in polynomial time relative to C. By that I mean that if you were to restrict your inputs to come only from C, then you can check in polynomial time whether the input graph belongs to this particular subclass D or not. Why is that so? Because it is extension preserved and FO defined, and because the class C satisfies Watchtowers theorem, you know that D is defined by an existential sentence. Now, this existential sentence can be really seen to be kind of holding within itself the description of finitely many graphs that are minimal with respect to inclusion in D. Which means that this existential sentence can be just unpacked to obtain a class of a finite set of graphs F that are minimal for D, which means that these graphs in F are in D and no induced subgraph of any of these graphs is inside D. Okay, so they are minimal with respect to inclusion in D. Furthermore, because this class is extension preserved, every graph inside D is an extension of one of these minimal graphs. Okay. So if with this property, now you can get a simple algorithm to check membership in D of inputs coming from C. All that you need to do is you take this input graph, you know that this this class F is just a finite class. Okay, it's just a fixed class when relative to D, it's just a fixed class. So therefore, the number of the graphs in F are fixed. The sizes of these graphs are fixed. There is a maximum size of all of these graphs. Call that size to be K. Okay, so you take an input graph from C. You want to know whether it is in D or not. Well, it's of size n. You just look at all n choose K subsets of size at most K from the graph. Okay, so that will give you a K size subset. You just want to check whether the graph induced by this K size subset is isomorphic to one of these graphs which is inside F. Well, F is a finite class. It's a fixed class. You can check for you can check whether this K-sized graph is isomorphic to one of these graphs in only constant amount of time. The number of such subsets that you need to range over is of the order of n to the K. Therefore, you get an algorithm which runs in C times n to the K, where K is a constant, and which checks for membership in D when you have the promise that the inputs come from C. Okay, and that shows that you have a p-time algorithm. So that is one immediate thing that Watchtowers theorem gives you. And for the same reason, it also serves as a structural meta theorem in the sense in the same spirit as algorithmic meta theorems, where such a structural meta theorem will give you uniformly finite excluded induced subgraph characterizations for any first order definable hereditary subclass of the class. So look at a first order definable hereditary subclass of C. Hereditary means that it is closed undertaking induced subgraphs. Okay, so look at such a class, call this class as E. Okay, look at the complement of this class within C. It is an extension closed class. It is first order definable via the negation of the sentence which defines this particular class E. So now we are back to looking at a class D, which is extension closed, which is first order definable. We already saw because C satisfies Watchtowers. There is only a finitely many minimal graphs that are there for D, and you can show without much difficulty that these finitely many minimal graphs for D are exactly the excluded set for the class E. Okay, which means E is defined via these finitely many minimal graphs of F by excluding them as induced subgraphs. Okay, and so that serves as a finite definition of D. Because of this reason, membership checking in E is also of course polynomial time. And furthermore, this particular such a result is of interest because, well, this is largely in the same spirit as such theorems were Robertson and Seymour in their famous graph minor series, where they showed that any minor hereditary class of graphs is characterized by a finite set of excluded minors. Okay, so this is replacing the minor relation with the induced subgraph relation, and you're getting these characterization theorems. So that's this is made possible by Watchtowers. Now, this particular characterization is for a hereditary subclass is within the class, but you can kind of get rid of this within the class to all graphs in some special cases. So for example, graphs of vertex cover number at most K. It's a very well studied NP complete problem, and also one of those important problems for parameterized complexity. This particular class of graphs is a hereditary class. You can show that it is first order definable. Okay. In fact, and you can show that this is a subclass of the class of all graphs of pre-depth at most K plus 1. Now pre-depth at most K plus 1 graphs satisfy Watchtowers, and they are themselves defined by finitely many excluded induced subgraphs in the setting of all graphs. So you can basically concatenate these excluded lists, and you can get a finite number of graphs in the setting of all graphs that defines the class of all graphs of vertex cover number at most K. So this result basically includes a similar such result that was proven by Lovash in the 70s. In the late 70s, and he had given a finite excluded subgraph characterization, but we have a more keener result. So of course now there are various proofs of this result which are combinatorial, but the first proof of this was model theoretic and using Watchtowers theorem. That shows the significance of this result for computer science. There are some more connections, but I'll restrict them to just this for now. Okay, now. We have been talking about Watchtowers over classes of graphs. What happens over the class of all graphs, all finite graphs? Okay. Well, it turns out that this particular theorem fails in the finite. Okay, which means that the syntax semantics correspondence that this particular theorem breaks. Okay. Now, when it breaks, it means that at least one of the two directions of this theorem fails. The syntax implies semantics direction stays to hold. In fact, the syntactic form of existential sentences always ensures that it is going to define an extension closed class for any class of graphs. But the semantics implies syntax direction fails. Okay, and this was shown by Tate in 1959. Showed that there is an extension preserved first order sentence okay, which it's extension preserved over the class of all finite graphs. It's a first order sentence, but it is not equivalent over the class of all finite structures. It's not equivalent over the class of all finite structures to any existential sentence, which means the class of all existential sentences is not expressive enough to be able to capture all extension preserved properties of finite structures. Okay. So this was shown by Tate in 1959. The kinds of structures that he considered were ordered graphs, which means you have graphs where you have an extra relation. Yes.
One question.
Yes.
So what you were saying is that this Los-Tarski still holds for the case of finite graphs, but not for arbitrary finite structures.
No. The classical Watchtowers theorem says that if you were to look at your underlying space of graphs to be all graphs, irrespective of cardinality, finite and infinite. Okay, and now you're looking at classes of subclasses of this class of all graphs. That means any class of graphs or any class of structures, finite or infinite, which is extension preserved. Which means that if you take a graph from the class finite or infinite, and if you take an extension of that finite or infinite, then that particular extension must be inside this particular class. Okay, if this is guaranteed of your class and if the class is first order definable, then definitely it is going to be the case that it is also defined by an existential sentence. Okay. Now, when you look at only finite structures, you're clipping off your view to only finite structures, which means you can have an extension preserved first order sentence, which is extension preserved, which you can have a first order sentence, which is extension preserved when you look at it only for finite graphs. But in the infinite is no longer extension preserved. Okay, so you have an example for this particular class that you're looking at, which is first order defined, but you have an infinite graph such that there is an infinite extension of it, which is not in the class. Okay. So the space of all, so the first order sentences which are extension preserved over all structures are certainly extension preserved also over finite structures. But converse, looking at extension preserved sentences over finite structures need not be extension preserved over arbitrary structures. Okay. And this fact is capitalized by Tate and various others to show that, look, this particular property, I can come up with a sentence which is extension preserved in this finite view, but it is not going to be described by any existential sentence. Okay. And this particular kind of structures that was looked at by Tate was ordered graphs. Okay. Now this particular result is, well, it's open for 59 years, so 60 years. I was looking at this and very natural question for such failure results is that, well, they are sensitive to the vocabulary. Yeah, they're looking at a class of structures, which is in this particular case ordered graphs. So one can ask, well, you're looking, maybe the failure is made possible because you're looking at a rich enough vocabulary. Yeah. What if you do not have such a rich enough vocabulary? Just if you were to look at only graphs, ordered, only undirected graphs, then can you still continue to show this failure? So this particular problem I raised in ICLA in 2019. And in 2021, Chen and Flum, they showed in the Alex paper that this failure continues to hold even over undirected graphs. So the idea is that they just translate Tate's sentence using interpretations, first order interpretations, existential interpretations, or what they call strongly existential interpretations, and they're able to kind of essentially translate that particular sentence into the realm of graphs. Okay, and then show this failure. So the failure does hold over undirected graphs. It is just only a very recent result. Okay, which means that there is an extension preserved first order sentence of graphs, which is not definable by any existential sentence. Now, because this failure has happened, which means that existential sentences are weak, they are not strong enough or large enough for extension preserved properties, you can say, okay, I want to recover this theorem, what do I do? Okay, so one natural thing would be, okay, your syntax is maybe restricted. So how about enlarging the syntax and saying with the enlarged syntax, can you subsume extension preserved properties? Okay, so that's one way of kind of recovering. That's what we are kind of going to look at. Now you observe that there are several enlargements that you can consider of existential sentences, but one natural one is that you observe that existential sentences do not have any quantifier alternations. There are only one kind of quantifiers. Okay, so how about if we were to allow more quantifier alternations, then can extension preserved properties be characterized or captured using more quantifier alternations? Okay. So to make this particular thing precise, let sigma n be the class of all first order sentences which have this form. They are in Prenix normal form, which means that they have a bunch of quantifiers, and then there's a quantifier free part. There's a quantifier spine, and there's a quantifier free part. And every first order sentence can be brought into this normal form. Okay. And now the spine looks like there are n blocks of quantifiers beginning with an existential block. So existential block for all existential, etc. and then you have a quantifier free part. This class of sentences is called sigma n. Okay. The complement of this particular class is pi n, where you once again have print structure n blocks, but you begin with a for all, and then you begin the alternation with for all. So for all exists, and so on. Quantifier free at the end. So this gives you these prefix. These are called prefix classes. Okay. And now you can ask whether is it the case that extension preserved FO properties can be captured using sigma n or pi n for some fixed n. A keener version of this particular question was posed by Rosen and Weinstein in '94. So they observed that Tate's sentence is, of course, first order definable, but it's also definable in a language called Datalog with negation. Yeah, this is a database programming language, and they observed that this particular sentence can be expressed in Datalog. Now, Datalog sentences, by very virtue of their syntax, will always define extension close properties. Okay, so existential sentences are special kinds of Datalog sentences, but Datalog sentences are a larger class. And now they are saying that, look, Tate sentence is a first order sentence which is also in Datalog, and it is not equivalent to any existential sentence. So is it now the case that first order sentences which are in Datalog, which therefore will be extension preserved because it is in Datalog? You want to know whether it is, they asked whether it is the case that some prefix class captures such sentences semantically. Okay, so is it the case that FO intersect Datalog is contained in sigma n or pi n for some n? Was the question that they asked. We kind of address this particular question, and we show that there is a negative answer to this question. And then
So
through a series of results. Yes.
One more question. So did you say something like a prefix closed? I did not fully get it.
Prefix class. Prefix class. Any sigma n and pi n are called prefix classes.
Okay. Okay. And how is Datalog related to the FO?
Datalog is a very good question. Good question. We'll come to that. I'll have a slide on Datalog. So Datalog is related to FO via the fact that it is incomparable with them. So every Datalog sentence defines an extension preserved property. There are fragments of first order logic which define extension preserved properties, like which are in particular existential sentences. But Datalog can, so already that means that, but first order logic can talk about things which are not extension closed also. Okay, so that already shows that there are first order sentences which are not in Datalog. Now, the other direction, you can show that there are Datalog sentences which are not expressible in first order logic by observing that reachability can be expressed in Datalog. Yeah, you have a graph, you want a query such that which has two free variables x and y, and such that it evaluates to true on a graph with 2 points given as instantiation for x and y, if and only if it is the case that there is a path from x to y.
So
okay.
Is it true that then you can express transitive closure, something like that, like transitive closure properties in Datalog, which I believe
in Datalog? Yes, you can. Yes. Yeah.
Okay.
So Datalog allows you to perform these transitive closure computations with it. Mm-hmm. So, but this cannot be expressed in first order logic.
Yeah.
So that shows the incompatibility of it. Okay. All right. So now. So we answered that question in the negative via a series of results. The first of these was shown in ICLA and then subsequently at CSL with Anuj. The first result is that if you were to look at if you look at pi2, after all, pi2 is of the form like for all exists, and then quantifier free. Now, if you were to stratify pi2 via the number of universal quantifiers that appears in it, yeah, and if you call pi2k as a set of all pi2 sentences with k universal quantifiers, okay, then you can show that there is a vocabulary tau, and there is a pi2k plus 1 first order sentence, which is in Datalog, which is Datalog with negation, which is therefore extension preserved over all finite structures. But this particular sentence is not equivalent to any pi2k sentence. Okay, so every existential sentence is a special case of a pi2k sentence where the number of universal quantifiers is 0. Okay, so all existential sentences are inside pi2k. So pi2k is a strictly more general syntactic fragment, but it's also strictly more general semantic fragment. And what this result shows is that this strictly more general semantic fragment is also expressively incomplete, is not expressively complete for extension preserved. In fact, even Datalog definable first order properties in the finite. Okay, so you have this more general syntax which also fails to capture extension preserved properties in the finite. So now. So that was
again. So any extension preserved property can be expressed using this Datalog negation. That's what you mentioned, maybe, or so if I consider any extension preserved property, can that be encoded in the Datalog as a Datalog formula?
No. So this is actually, this is one of, if you're looking at, I would even think, so any extension preserved property certainly is going to have a certain number of minimal elements, which could be finite or infinite. If it is finite, then it is definitely definable in first order logic. The only cases of extension preserved properties that are not expressible in first order logic are those that have infinitely many minimal elements. Now, whether such properties are expressible in Datalog is in fact no. Well, it's an open problem. In fact, just first order definable extension preserved properties, are these always describable in Datalog?
Okay.
Is, to the best of my knowledge, open.
Okay. Okay.
So therefore, if you were to intersect first order logic with Datalog, okay, then you're looking at that fragment of first order logic which you know is Datalog expressible.
Okay.
Yeah. Now, can you say that it's not in some prefix clause? That is the kind of question. But the question of whether general extension closed even first order properties, whether they are in Datalog, to the best of my knowledge, I think is open.
Okay. Okay. But as long as it is first order definable, it's included in the Datalog negation.
No. First order definable properties.
I mean, first order definable these extension closed properties are Datalog definable.
No, that is an open question. That is itself an open question.
Okay.
First order definable properties are extension closed, whether they are always describable in Datalog is open.
I see. Okay.
So yeah. So you want, yeah. So that is still open.
Okay.
So you consider the intersection with Datalog, so that you get a fragment of FO and Datalog, and now you want to know whether it is describable in some syntactic, some prefix clause. So at least this particular thing shows that this particular fragment FO intersect Datalog certainly cannot be inside pi 2k, yeah, because you have a counterexample. Okay.
And
now
when you are talking about when you are talking about vocabulary tau, it's not necessary that you are talking about the vocabulary of graphs, right? It can be some other model.
Yeah. That's right. In this particular example, this is the vocabulary of ordered graphs with two constants.
Okay.
Whether it is the case that you can still encode this particular example in the vocabulary of graphs is open. It remains to be done. It is in fact connected to one of these open questions that I will raise towards the end.
Mm-hmm.
Okay. So far, we are utilizing the power of vocabularies, but not too much. Okay, so this particular thing shows that pi 2k is expressively not sufficient for extension preserved FO intersect Datalog properties. But now you observe that the counterexample for pi 2k is in pi 2k plus 1. Yeah. So now, therefore, you can say, how about taking the union of all these pi 2k's, that will kill all counterexamples, because all counterexamples are, of course, are in pi 2, are after all in pi 2. So how about looking at the class pi 2, okay, and proposing and examining whether pi 2 is expressively sufficient for FO intersect Datalog queries, okay, and that roughly around the same time as this. In fact, soon after submission, I realized that, well, Tate's example itself is an example of a sentence which is Datalog in FO. In fact, it is in sigma 3, but it is and it's therefore extension closed, but it is not equivalent to any pi 3 sentence. So not just pi 2, but even pi 3 is expressively fails. It's not powerful enough to be able to capture FO intersect Datalog queries in the finite. Okay, so now the natural question is this an instance of a more general phenomenon? Yeah, what about pi n? And so that, we indeed show. So that's the result with Anuj at CSL last year. So that for every n, there is a vocabulary sigma n, okay, some vocabulary sigma n, and finite vocabulary. And in fact, the vocabulary will contain only binary and unary predicates. That also, so it's like a multi-graph, yeah, colored. So there's a vocabulary sigma n and a sigma 2n plus 1 intersect Datalog with negation sentence that, of course, is extension preserved over all finite structures, but is not equivalent to any pi 2n plus 1 sentence. And likewise, for every n, there's vocabulary sigma n and a pi 2n intersect Datalog sentence, which is extension preserved, of course, but is not equivalent to any sigma 2n sentence. Okay, so which means for whichever n you consider, sigma n or pi n is not sufficient, is not powerful enough to be able to capture extension preserved properties in the finite. Yeah. So there's an extra bit about these two results. Can you just give me a minute? Just give me a minute. Yeah, sorry for that. Right. So yeah, so I'm saying that these two results are tight in a certain sense, in the sense that the example is a sigma 2n plus 1 sentence, which definitely, of course, is describable in sigma 2n plus 2 and also in pi 2n plus 2. Yeah.
So, Abhishek, can I ask a more general motivational question here?
Yeah, sure, definitely.
So, of course, pi n and sigma n are, without any restrictions are not, contained. They are orthogonal, right?
Yes, exactly.
I mean, this is odd. Now, by putting these conditions on being in Datalog with negation and being extension preserved, why would you hope to connect these two classes? I mean, what is the motivation for looking at asking this question? I mean, is it that because it is in Datalog and extension preserved, you have some hope of getting it into the symmetric, I mean, the dual class?
Well, that was the hope that of Rosen and Weinstein. I mean, they asked this question of whether it is the case that if you put the Datalog restriction on first order logic, then can you always get them to be subsumed in some prefix class? So that was their question.
And you at least ruled out the dual class. Yeah.
We have ruled out both classes. I mean, we show that both of these results kind of cumulatively show that whether you take sigma n or pi n, none of these for any.
Okay.
None of these is going to be expressively powerful enough to capture extension preserved property.
Thank you. Thank you.
So these two results are in a certain sense tight because sigma 2n plus 1 properties are obviously expressible in sigma 2n plus 2 and pi 2n plus 2. And you show that this particular result shows that it is not in sigma in pi 2n plus 1. So both of these results are in a certain sense tight. But in cumulatively, what these two results are summarily saying are that no prefix class of first order logic is expressive enough to capture extension preserved FO properties in the finite, and even FO intersect Datalog with negation queries in the finite. Okay, so that shows the expressive limitations of prefix classes with respect to extension preserved properties. So what I intend to do for a good part of this talk is the remainder of this talk is to give you an idea of how we go about proving these results. We will look at the specific example of Tate's sentence, okay, and analyze it in full detail, because the general result is only a kind of a self-similar version of Tate's sentence. It's only bootstrapping on Tate's sentence and doing similar kinds of constructions at a higher level. So Tate's sentence alone will provide all the template for the reasoning beyond. Okay, so that's what I'm planning to do. If you have, is there any questions at this particular point in time? Okay. So if there aren't any, let's so these are the two results that we look at in the talk. So Tate's theorem, and then for this general thing, generalization is only going to be a analogous thing for Tate. Okay, so Tate's sentence. What is Tate's sentence going to look like? So this particular, so Tate's sentence is what I denote as sum total R for good reason. This particular sentence is over the vocabulary which contains three binary predicates, less than, R, and S. Tate's original sentence had only two binary predicates, less than and R, but for the purposes of exposition, we have split up that R into two parts, R and S. Okay, you can kind of coalesce the two together later on to get more optimal, but we have three binary predicates now. Sum total R is over the vocabulary less than R and S, and it is an implication whose left hand side is saying that less than is a linear order. Okay, which means that less than is reflexive, it is antisymmetric, it is transitive and total. All of this is definable in first order logic using a universal sentence. Second part says that that partial successor is true, which and that means that for every U and for every V, whenever it is the case that U and V are connected via an S, it is indeed the case that V is the successor of U with respect to the linear order, which means that for all U, for all V, if S of UV is true, then it implies that there is no Z such that Z is distinct from U and V, and Z lies between U and V in the linear order. So this description is a first order description, okay? And that is what is partial successor. So in other words, we are saying that whenever S is true, it is consistent with it defines the successor relation. But it's possible that you have 2 points U and V such that V is the successor of U, but they are not related via an S. That's perfectly fine. So that's why it is a partial successor relation. Whenever it is true, it defines it is consistent with the successor relation. So that's partial successor. And then the last condition is R total UV, which just says that R total UV is true if there is an R edge from V to U. Okay, so that defines an interval now between V and U. Okay, and the statement says that between V and U, the S relation is a total successor relation, which means any 2 points that are there between V and U, if one is a successor of the other, then definitely it is the case that it is related to the first, its predecessor by S. Okay. So this is what R total UV says. You can describe this in first order logic. Oh, I do have the first order definitions for this in the next slide. Yeah, you can describe this in first order logic by saying that RV of RV comma U is true, and for every Z between U and V and less than V, it is the case that there is some W which is ahead of Z, such that S of ZW is true. Just this particular condition, in conjunction with the fact that S is consistent with the successor relation of the linear order, automatically means that between U and V, R total UV implies that S is going to be a total successor relation. Okay, so all of these are first order definable. That gives you sum total R. That you can put these first order definitions together and see that sum total R is in sigma 3. Okay, so that shows that this particular sentence is in sigma 3. We will now see that this particular sentence is also definable in, so this is state sentence. This is state sentence in essence. We want to show the following things about it: that it is definable in Datalog, that it is and therefore it will be extension closed, and that this sentence cannot be defined in pi 3. Okay, these are the two things that we'll show.
Okay, sorry. Can we just go back to the previous slide? I was wondering, how do you get the sigma 3? I mean, essentially there should be an exit and then there will be some for all and another exit, right?
Exactly. So you look at the right hand side of this implication. Oh yeah, I can have the pen. Look at the right hand side of the implication. You have this guy. Yeah. So this is exists.
Okay.
R total UV this is quantifier free. This is for all. And this is exists. So when you kind of put this in Clinics normal form, this is something of the form for all exists.
Okay.
Yeah. And then you have exists for all exists. That's sigma 3.
Okay. Yeah. Thanks.
All right. So that's okay. Okay. So now just to get an idea of what kinds of things that it can define. So here is a particular kind of structure. There's a linear order. These S relations are defining the successor relation indeed by definition, and you have these R predicates. So you want to know whether it is a model or not. Well, linear order is of course definitely true because we kind of defined it that way. Partial successor is of course always again true because that's how we define this particular model. But let's look at R total. Let us look at all those candidates U and V which can satisfy R total. They must be related by an R. So either it is this guy. But if you take the endpoints of this particular R segment as V, then you have this kind of middle thing, which with the marked red thing, which witnesses the failure of the totality of R, totality of S. So that goes away. You have another candidate, but that again fails because the first at the very beginning you have the failure of the totality of S. But there is one candidate that does go through, and this is that indeed taking U and V as the endpoints of this particular segment. You have R total UV as true, so this is definitely therefore a model for sum total. Okay. Now here is Datalog definition for takes. And what is Datalog? So Datalog is a database programming language. I think it might have been probably sometime in the 80s where it was introduced. And Datalog syntax has has this following form. A Datalog rule, a Datalog with negation rule, is of the following form. Either it is of the form R of x bar, left arrow a x1 bar. So there's an LHS and there is an RHS to the rule. The LHS is a predicate. Yeah, it's a predicate with some free variables. The RHS is either an atomic predicate or its negation. Okay, so it's A is either an atom or its negation, and this atom could be equality as well. Yeah, so for example, A could be E of xy, or x equal to y, or x not equal to y. Okay, that is an example for it. So that is one kind of a rule. Another kind of a rule is where on the right hand side you have R of x1 bar, R of x2 bar, R of xn bar, where each Ri is either an atom or a negated atom, equality of negated equality, or a predicate which appears unnegated. Okay, so there are two kinds of predicates: those that are appearing at the atomic level and those that are appearing at a non-atomic level. The non-atomic predicates must always appear positive. The left-hand side, all the predicates appear positively. On the right-hand side, if it is an atomic predicate, then it can appear negatively. But if it is a non-atomic predicate, it must appear positively. Okay. So that's the syntax. The free variables on the left-hand side are a subset of the free variables on the cumulative set of free variables on the right-hand side. And that's your, so that defines the Datalog rules. And a Datalog program is just a finite set of Datalog rules. Now, the reason for calling it Datalog with negation is because you're allowing negation at the atomic level. The traditional Datalog did not allow negation at the atomic level. It is just only positive. It's just fully positive. Because it is fully positive, it has some other properties like closure under homomorphisms. But if you allow negation, you do have that a Datalog program always defines extension close properties. This is simply by virtue of the syntax and the positivity of these non-atomic predicates. That's what makes for this extension close. And this is incomparable with FO as we saw earlier already. Okay.
So
that's your Datalog.
This may be a very stupid question. I mean, it looks very similar to Horn clauses, right? I mean,
yeah.
So I was just wondering, yeah, like what kind of differences you would have compared to a Prolog program, for example, or. Horn clauses, of course, are in the context of satisfiability. Of course, you have a certain semantics for these clauses because you know that they are of this implicational form, right? They are like A and A1 and of AI implies B. That's the Horn clause. Yeah.
So we have this kind of implication, and this is like a SAT formula. Whereas there is a semantic. This particular thing is not a. I mean, this implication is not a logical implication. It is a rule.
I see.
Okay. It is a rule of the form which has this denotation where you have this implication, but this arrow is not to be understood as implication. Okay. But there is a way of translating all of this particular thing into a first order, into a it's an existential least switch point logic sentence that you can translate these kind of sentences into. Okay, but this implication is not that implication. So that way, the apparent writing form is the same, but the semantics.
Okay, thank you.
Okay, so that's Datalog syntax. Very simple. Okay, and now the claim is that you can describe sum total R using a Datalog program very easily, actually. So what we just need to do is just express negation LO, negation partial successor, and as Datalog with negation programs with start symbols LO, not partial successor, and R. Then the Datalog program for sum total R is just these three rules. Sum total R on the LHS and not LO. The next sum total R on third rule is not sum total R and R total D. Okay. So that's the program, and so sum total R. So LO, well, not simply. So you have already seen that LO has a universal definition. So the definition of an existential sentence. Existential sentences have a simple Datalog description. All these things which are in the matrix part of negation as RHS of the Datalog rule that corresponds to this particular sentence. Okay, that's a simple description. Likewise for partial successor. Partial successor also is an negation of partial successor is also an existential sentence. Once again, you can kind of club all of these matrix parts together. Yeah, you can just club all these guys together and you get this particular form. Which is a very simple description of any existential first order sentence. That is for that. Now, the last part, which is R total, is the one where you really utilize Datalog. You know, the power of Datalog, which is otherwise beyond it. Okay. So when you're saying that R total UV, so you're saying V and U, there is an R, and then S is V. Okay. And we have this first order definition. Well, this first order definition has a quantifier switch. So, you know, it is not existential. It looks complicated. How do we write this particular thing in Datalog? Well, you observe that this particular can be equivalently understood as saying you can reach from U using S, hopping using the S edge. So in other words, it is talking about reachability of V from U using S as the edge relation. Okay, and this is like the canonical database query. The most standard Datalog is reachability, and that's exactly what this particular thing is expressing. And so therefore you have a natural Datalog sentence for R total.
So since
sure.
you were talking about this kind of reachability, which sounds very similar to this STCon. So I was just wondering, is there any relation between NL and Datalog, the kind of formula that you can describe captures the class NL, or is it a subset or anything?
I am afraid I can't see quite why it must be the case that, well, so the claim is you're saying that is there a result which says that NL corresponds to Datalog.
Yeah, that's what
I would think no. I would think no.
Yeah, possibly because also that Datalog does not capture the whole of FO, maybe also. I would assume that FO should be something like a subset of NL in some sense.
Yes, that's right. And Datalog is already not enough. That's correct.
Okay.
Another way of saying it is that Datalog always defines extension closed properties, but NL you can of course get arbitrary classes which are not extension closed.
Mm-hmm.
You can, for example, any finite class which contains incomparable elements is going to be not describable in Datalog, but of course in constant time and constant. So you will have this.
Okay. Thanks.
So that's a good question to see the descriptive complexity of Datalog. Maybe there's some work on this. I'm not aware.
Okay. Thanks.
Okay. So that now let's okay. So that basically shows that you have this Datalog program. You have the extension closure of sum total R. Now we are now proceeding towards the proof of the result, which shows that sum total R is not going to be describable in Python. Okay. Towards this, the first thing that we want to do a sanity check. That is it the case that we have shown the extension preservation of this particular sentence in the finite? Is it extension preserved already in the infinite? If it is extension preserved already in the infinite, then by Watchtowski's theorem, classical Watchtowers theorem, this is already going to be equivalent to an existential sentence in the infinite, and therefore also in the finite. Okay, that right away kills this any hopes of getting this particular sentence to be a counterexample. So let us do the sanity check, and let us indeed verify that this is not extension preserved in the infinite. This is exactly what we're using, that it's not extension preserved in the infinite to be able to make it a counterexample. Here is a model, and here is an extension of that. The model is, you take the model A, just normal numbers, 1, 2, 3, 4 natural numbers. Infinity called omega. Okay, and ordering J, where J, which is the usual ordering of natural numbers, and all these numbers are omega. Total order on all these elements. There is a back RH from omega to 1 as the usual successor relation. Observe that there is no successor, there is no predecessor for. So therefore, by this very definition, you see that S is a total successor relation on A. Look at the extension of A, which is B. In the infinite, you add a point called omega prime just prior to omega. Okay, so you have inserted a point called prime in A just omega, and you have no S edge from omega. Everything else is the same. Yeah? So A is now a substructure of B. So B is an extension of A. Okay. Let us now verify what happens to sum total R on both of these. Linear, both of them satisfy. Fine. That's all. Successor relation. Well, whenever you have S relation defined, it is a relation that is by these structures. There's some lag, I think. Yeah. But now look at. I think there's some lag between. Let us look at R total. Well, the only way by which you can make R total true in A or B is by choosing these points 1 and omega. All right. So now we are asserting if R total has to be true, we are basically saying that the S relation must be a total relation on this entire structure. Well, that is true in A, but well, that is not true in B. Yeah, because so we have the first order definition of R. Yeah, and we see that because of the fact that we have omega prime, which has been inserted prior to omega without the S edge. The totality of the S relation has been broken. Yeah. So B does not satisfy the fact that R total UV is true, R total 1 omega is true, but A does satisfy this fact. Okay. So therefore, A is indeed a model for sum total R. but B is not a model for sum total, despite the fact that B is an extension of A. So the sentence is not closed under extensions in the internet, but it's closed under extensions in the finite. Okay. Okay. Any questions on this? All right.
So
There are then
just a small comment, like we have around 10 minutes.
we do have only 10 minutes.
I mean, if you can
But
take
we oh, I see. But we already had question answer session interspersed in the
okay,
past.
I think you can take another 5 minutes.
Yeah, but it's okay. But I think I'll be able to accelerate. I think yeah, we'll be able to accelerate. Okay, so here is the theorem. So the sentence sum total R is not equivalent to any pi3 sentence. To be able to show this, here is what we do. Let sigma nk be the class of all sigma n sentences in which every block has k quantifiers. Okay, define pi and k analogously. Okay, sigma n is just the union of all sigma nks. Define pi and k analogously. Define this relation called right arrow n comma k as being true of A and B. If it is the case that every sigma nk sentence true in A is also true in B. You can see this particular relation as contrapositively as A and right arrow n comma k B is true if it is the case that every pi nk sentence true in B is also true in A. This is simply because sigma nk and pi nk are related via negation. Okay. Now what we're going to do is for every k, we are going to construct a model mk and a non-model nk of sum total R such that nk right arrow 3 comma k nk. If this particular relation is true, the claim is that sum total R cannot be equivalent to any pi3 sentence, call that as theta. Suppose it was equivalent to a pi3 sentence theta, okay? Because nk is a model and because a model of sum total R and because sum total R and theta are equivalent, mk would be a model of theta. Now, because of this 3 comma k relation, every pi 3 comma k sentence true in nk is also true in nk. So therefore, theta will be true in nk. But theta is equivalent to sum total R. So therefore, nk is a model of sum total R. That's a contradiction. Okay. So therefore, if you have this particular condition, if you have nk, a model nk and a non-model nk such that this relation holds, then it follows as a consequence that sum total R cannot be equivalent to any pi 3 comma k sentence. Okay, if you show this for all k, then you have basically ruled out all of pi 3. That's exactly what we show. We illustrate our constructions for k equal to 3. So before that, here is a quick definition which is rather intuitive. An ordered sum of two ordered structures A and B is just obtained by taking the disjoint union of these two structures, placing all the elements of the first structure before the other structure, and coalescing or merging the last element of the first structure, the first element of the other structure. So you have A and B, and you look at the last element of A, look at the first element of B, kind of merge them together, and then you just put them to put the two structures together, you get the ordered sum. That's the intuitive understanding of ordered sum. Also, there are some variants of this, but this is how we understand it in our talk. So here is how MK and NK are constructed. Okay, they're constructed inductively using some substructures. The most elementary, the most basic substructure is the linear order L8 on 8 vertices. Yeah, it's just 8 vertices. Then you have the S relation, which is the total successive relation. G8 is obtained from L8 by removing the middle S relation from this thing. So you get rid of this guy, okay, and that gives you G8. Now, once you have constructed these two, you look at the structure tot3, which is just going to be an ordered sum of 7 copies of L8, okay, with an ordered sum on the left with L2 to the power 6 and on the right with L2 to the power 6. So it's sufficiently large, and then you connect the first and the last points particular relation R. Once you have constructed tot3, you can construct gap3 by replacing this particular guy G8. Okay, so it's exactly replaced by the substitution by this kind of switch in G8. That gives you these structures. Now with this you can now construct M3 and N3 as follows. Suppose you have gap3 constructed, you have tot3 constructed. Construct the structure called gap3 plus, which is the ordered sum of 2 to the power 9 copies of. Okay. Now you construct N3 in a similar way as tot. You construct this as the ordered sum of like 7 copies of gap3, and then you have gap3 plus, and then you have gap3 plus on the flanking the ordered sum of these. And M3 is constructed by replacing the central guy with tot3. Okay, of these structures. And the claim that I'm now making is that M3 is a model, M3 is a non-model, and M3 is 3, k related to M3, and that will complete the proof. Okay, here is how. Model relation is rather easy to see because, well, you have these structures and then linear order, of course, that's by definition, that's true in both of these structures. The successor relation, partial successor is true by definition in these structures. Yeah, that's again fine. But now let us look at R total UV. If we want R total UV to be true, it must be the case that U and V must be chosen as the endpoints of gap 3 or tot 3, a gap 3 segment or a tot 3 segment. Yeah, that's where you can find the R relation. Yeah, in M3, if you were to choose U and V to be the endpoints of the tot 3 segment that is there in M3, then, well, inside this you find, if you just look at what tot 3 is saying, tot 3 is just saying it is just an ordered sum of several copies of several copies of this linear order L. Yeah, but L, within this particular substructure L, you have the S relation to be total. Yeah, so therefore it is indeed the case that in tot 3, the S relation is consistent. It is a total successor relation of with respect to the linear order in tot 3. So therefore you have a witness for U and V, which makes R total UV true in M3. So therefore M3 is a model for some total R. But in M3, you will have to choose U and V as always the endpoint of a gap 3 segment. But now let us look at this gap 3 segment by its very definition. In the gap G8, yeah, that's a G8 segment here. But in G8, you have this gap. Okay, yeah, that shows that the successor relation gets broken inside gap 3. And since all copies of gap 3 are isomorphic, it means that there is no way of choosing U and V such that R total of UV is true in N3. That shows that N3 is a non-model for yeah. So you have that you have this thing up here. Yeah. And so that basically shows that one is a model and one is not a model. All right. And now on the which is about showing this 3, k relation. All right. Here is what we use. It's a very classic thing called the Ehrenfeld fragment. Yeah, it's one of the very important from model theory which works both uniformly in the infinite and the finite. There are various versions of this particular game for different kinds of relations. So here is one for our relation. It's not a characterization, but one that implies this particular relation that we have. So you have two players called spoiler and duplicator. Okay, and you have a game arena which consists of a pair of structures A, B. Okay, the number of rounds is n. The two players are called spoiler and duplicator. They are alternatively sometimes called Samson and Delilah. Okay, and various other names. But I think in the Indian context, it might be very appropriate to call them Shakuni and Draupadi. Yeah, because after all, played in the Mahabharata, and indeed Shakuni was the spoiler. Draupadi, though not directly involved in the game, was certainly indirectly involved, and so she was played. But he won unfairly then. But in this, in our age, in this yuga, Draupadi will have a big comeback, as we see that duplicator will actually win the game in all the structures that we're playing. So, but for the purpose of this talk, we'll follow the standard notation. We just call them a spoiler and duplicator. So this particular game says that in the odd rounds, spoiler chooses a tuple from A, k tuple from A, even rounds from B. Duplicator does the other thing. In the odd rounds, he chooses from she chooses from B, and in the even chooses from A. At the end of it, you have at the end of n rounds, you have n tuples from each of these structures. You say that the duplicator wins this play of the game if your view of these two structures relativized, restricted to only these chosen tuples, forms a partial isomorphism. Please, Clark. I'm sorry. So anyway, that's the winning condition. This partial isomorphism condition is the winning condition for the duplicator, and she has a winning strategy if she wins every play of the game. The claim is that if the duplicator has a winning strategy in this game, then it must be the case that A right arrow NK B is true. So therefore, for our purposes, to be able to show that NK is 3K related to MK, we can just show that in the game that is played between the two structures, the duplicator is a winning strategy, and that's exactly what we'll do now. To do that, we will utilize one more little model theoretic bit, okay, which plays a key, which is that there are some composition properties that hold true for this particular relation. If you have A and B that are related via this NK relation, then if you join the endpoints of A and B with R, then the NK relation continues to hold between the new structures obtained. If you have, I suppose there is a bit that is there here which is missing. If you have A1 and A2 with A1 to AI and AI plus 1 to AK, and you have B1 to BI and BI plus 1 to BK chosen in A1, A2 and B1, B2, then if you kind of take the ordered sum of these two structures and you take the ordered sum of the B structures, okay, then and expand it with these elements, then this NK relation basically transfers. Yeah. So if you have the NK relation 2 between pairs of structures and another pair of structures, you kind of put the two structures at the top, put the two structures at the bottom, then you still have the NK relation to be true. It's a very composition property, which actually plays plays an immense role in a number of things, including outside of this context. Okay, so that is one. And the last, to take sufficiently many copies of any particular structure, ordered sum of sufficiently many copies of any ordered structure, then any two such copies, any two such ordered sums will be NK equivalent. Yeah, in particular, this relation goes both ways. This NK relation goes both ways. Okay, now with that, we are completely armed and equipped to do our let's play. So we have G8 and L8. We want to show that the duplicator has a winning strategy in the 1,3 game between G8. The game proceeds by the spoiler or Shakuni picking up a 3 tuple from G8, and the duplicator has to respond with the 3 tuple such that the partial isomorphism condition is true. So here is, suppose this particular was the choice, then well the L8 the duplicator just mimics that choice. Yeah, that automatically gives you a partial isomorphism. If the duplicator picks up, if the spoiler picks up that particular choice, yeah, then it is the case that you mimic that particular choice. The duplicator mimics the choice. But now here, if in this possibility, if it is the case that the spoiler picks up A1, A2, which do not have this S edge, you observe that in L8 you cannot choose successive elements. There is always an S edge between two successive elements. But what you can do is a shifted choice. Yeah, you can just shift A2 and A3. Yeah, so that this linear ordering is preserved, and of course there is no S edge between any of these chosen points. So that shows that the duplicator once again wins. So there is a winning strategy for the duplicator, and G8 1,3 L8 is true. We will utilize this to lift this to showing tot 3 is 2,3 related to gap 3. Okay. Once again, the spoiler makes a choice in tot 3. Yeah. And via a similar argument, you see that because there are too many elements here, there will be some gaps. Particularly, you would have these gaps between elements. Yeah, you can choose the duplicator just chooses one of these gaps, say this one, the first one. Okay, and now the duplicator organizes this tot 3 in 3 parts. The middle part, which is the middle, the boxed L8, there's a part to the right. Okay, and gap 3 analogously to these 3 parts. Gap 3 has a natural split up into 3 parts. There is G8, there is a part prior to G8, there is a part posterior to G8, and these will be the analogous. These will be the corresponding segments in these two structures. Okay, so these are the corresponding segments, and with correspondence, the idea is to kind of break up the structure into each of these structures into these 3, play the game individually on them. Okay, so once you have these 3 parts. You have this. You observe that. So this is A1 with an element little a1 chosen. You observe that A1 is a linear order greater than L 2 to the 6 points, and likewise B1. We have already seen in the composition properties section that two such sufficiently large linear orders will have the 2,3 relation true of them. Because of which the choice of A1 made in capital A1 by the spoiler will have a response by via the element little b1 in such a way that the game can further be continued for the duplicator to eventually win. Which means that the structure capital A1 expanded with little a1 and the structure capital B1 expanded with little b1 is such that B1 is 1,3 related to A1, A1. B1, B1 is 1, 3 related to A1, because the duplicator can still continue to play the game to win the game eventually. So you have this particular relation. Likewise, on the other side also, you can show that this relation is true. Okay, there is a choice of elements in B2, namely A2, B2, and B, so that this 1, 3 relation is true. And of course, in the middle segment, we just a while back showed that G8 is 1, 3 related to L8. So we have shown this particular 1, 3 relation to hold on these individual parts. Then now stitch all these parts together using the composition property that we saw earlier. Okay, you take the ordered sum of these, you take the union of all these elements, and the claim is that this particular structure that you have in the structure in the lower structure, you have a choice of elements, which is the cumulative response for the elements chosen by the spoiler in the first round of this game between dot 3 and gap 3. Because the duplicator always has such a response, the duplicator is a winning strategy, and therefore you have this relation to be true. Okay, and now the same thing is now repeated at the level of so because in the previous structure you did not have this back relation, but of course once you have shown this relation to be true, you can put in the R and you can get dot 3 is 2, 3 is related to gap 3 via the 2, 3 relation. Exactly the same argument for N3 and N3. I will not describe. I'll just show you the pictures, and you can see what's happening. You have this choice. You have these gaps. Choose a certain gap. Organize the structure into 3 parts, and look at the corresponding parts in both of the structures. Play the game on these. Stitch them together. Get the responses. Stitch them all together. Okay. So yeah, that's exactly that. A1, A2 has a response B1, B2. On the other part, you have a response B3, and on this part we just argued just a while back that dot 3 is 2, 3 related to gap 3. So we take these parts, we stitch them all together. We have a choice. We have response of the spoiler in the lower structure. A response of the spoiler in the lower structure for this choice of elements made by the response of the duplicator choice of made by the spoiler in the top structure. But since there is always such a response, the duplicator is winning, and that therefore shows that N3 is 3, 3 related to M3, and that's exactly what we wanted to show to complete the proof. Okay. So this completely shows that sum total R, which we saw was sigma 3 intersect Datalog with negation, is of course extension preserved, but it cannot be equivalent to any pi 3 sentence because the existence of such structures Nk, Mk, which have this relation for every k. So that's all. I think in the interest of time, I was wanting to just flash the slides of what happens at the general level. It is absolutely analogous. Okay, so this is the general thing that we want to show, that there's a vocabulary sigma n, and there's a sigma 2n plus 1 intersect Datalog negation sentence, which we will call sum total Rn, which is extension preserved, but is not equivalent to any pi 2n plus 1 sentence. If you put n is equal to 1, you get exactly the previous result. The construction is completely self-similar. So I just show you the slide. So this is sum total R1, which is just exactly the Tate sentence. Okay, and that is sum total Rn, which is exactly a generalized Tate sentence. Okay, which is just with these generalized definitions of partial successor and R total, where instead of having, so first condition is fine. The second condition, which says partial successor n, instead of having a quantifier free predicate that relates U and B, which was S1 or S earlier, now we have a quantified thing that relates the two. Okay, it is a generalized successor in relation, which we will come to, but assuming that you have defined that, you're just saying that partial successor is going to say that whenever you have 2 points U and B colored with Pn, a new predicate. So the sentence sum total Rn is over a vocabulary which is cumulative, which gathers the vocabulary of sigma n minus 1 and expands it with 3 more predicates, Pn, Rn, and Sn. Pn is unary, so it's like coloring the vertices. Rn and Sn are 2 binary predicates. So it is over this vocabulary, and the partial successor relation is just going to say for all orange colored points, all Pn colored points, it is the case that if V is related to U via the generalized successor n relation, then V is indeed the Pn successor of U. It is indeed the orange successor. It's not necessarily that it is the successor, but it's the orange successor of U. Okay, so we relativize this view to all these colored points. So and this successor n predicate is just simply saying that, well, the 2 points are U and V are colored orange. There is the atomic Sn relation between them, and it is the case that in the interval that is in the interval between, if you look at the interval between U and V, and you induce the original structure on this set of points between U and V, then the resulting structure satisfies sum total Rn minus 1. Okay. So this is the generalized successor n relation, and R total n is defined completely analogously as before. So with this, once you have this particular definition, the construction of, so this particular sentences can be seen to be first order and in sigma 2n plus 1. Okay. And the construction of the structures is also going to be analogous. At the atomic level, you have exactly these L8, G8, gap 1,3 and gap dot 1,3, and you have M13 and N13. Okay. You have this. This is happening at the base case. This is exactly Tate sentence happening at the base case of this generalized construction. Okay. And once you have this, you can show all of these relations to be true. The 1,3 relation on the left hand side, the 2,3 relations between dot 3 and gap 3, and the 3,3 relation between M13 and N13. Once you have these things, then you can and you can show that M13 is a model of sum total R1 and N13 is not a model of sum total R1. And once you have this, suppose inductively you have defined n minus 1, 3 and n minus 1, 3. Okay, you define this ordered sum, sufficiently large ordered sum of several copies of n minus 1, 3. If n minus 1 is p, define several copies, ordered sum of these, and attach these headphones to each of these copies. So this SN headphone, okay, to all of them, and then you construct tot n3 as the ordered sum of 7 such headphone copies of n minus 1, 3, and padded on both sides by suitably large n's, and replace in tot n3, replace the central copy with mp3. Indeed, a very musical construction. Okay. So we do this likewise. We just lift this construction back to Mn3. This is exactly the same for these generalized notions of tot and gap. And what we are able to show is that if you have this construction, if you have NP3 is 2p plus 1, 3 related, which means 2n minus 1 related to MP3 as induction hypothesis, then tot n3 is going to be 2n, 3 related to gap n3. And Nn3 is going to be 2n plus 1 related to Mn3. And likewise, if MP3 is a model of sum total R and NP3 is not a model, then you can show that Mn3 is going to be a model of sum total Rn, and Nn3 is going to be a non-model of sum total R. And that's exactly what you wanted to show. That exactly shows all that you need to show for showing the generalized result. Okay, so that basically completes. So here is the conclusion. So these are the main results that we saw. Okay, so Tate's theorem, Tate's sentence is so far was known for all these years to only be not equivalent to a universal sentence, but we strengthened the result to its optimum to show that it's not even equivalent to a pi3 sentence. And of course, we generalize that result to be eventually able to conclude that no prefix class of first order logic is expressive enough to capture extension preserved FO properties in the finite and FO intersect Datalog queries in the finite. This answers the open question from Rosen and Weinstein in '94. Future directions, well, I have not, so sum total Rn, of course, I did not dwell on it for too long, but nevertheless, in that brief, blinding speed with which sum total Rn was presented, sum total Rn is over a vocabulary which grows with n. Yeah, you observe that at every stage we put in 3 new predicates. Okay, so, and furthermore, this vocabulary is just only binary or unary. So it's just the vocabulary of ordered graphs. Ordered vertex and edge colored graphs. So the question now is there a fixed vocabulary which does not grow with n, okay, such that all prefix classes, prefix classes fail to capture extension closed FO properties that are written in this vocabulary? So is there a fixed finite vocabulary independent of n? Okay, that's one question. The second question is, can we get this particular result of prefix classes failing to capture extension closed properties, FO properties, of just undirected graphs? Possibly vertex colored. This is exactly what Shivashish, you were asking at the beginning. That what happens for undirected graphs? Do we have such a result for what happens for Tate sentence and what happens more generally? So these are the 2 natural questions that are there, and one of these we are able to resolve. We show that yes, there is a fixed vocabulary. You can all these extra predicates that we introduce can be simulated using smaller predicates. Can be simulated using just a fixed number of predicates. So it's the same construction, but you just optimize on the usage of these predicates. You can get the predicates down to just 4. Okay, so the challenge is, and so that's the first question is true. Second question, we still do not know. It would be very nice to answer this. We do, well, this Licks paper by Chen and Flum, Chen and Flum, does show that universal sentences or existential sentences fail to capture extension preserved properties. Maybe the result, maybe at some point they do also mention that you can even extend that to pi 2. Pi 2 is not expressive enough to capture all extension preserved properties of graphs, first order properties of graphs. But well, what happens for general n? So the hope is the intuitive answer for this is that it's going to be a negative answer, that or rather for this particular question, as it's stated, is positive, that prefix classes will fail to capture extension preserved properties of undirected graphs, but that is something to be shown. That's an open question to work on. All right, I'm nearly done. Oh, Professor Pandey has a question. Yes, Professor Pandey.
Nearly done. Why don't you finish? And then we can take it.
Oh, okay, I'm nearly done. Yeah, exactly. I have just one epilogue, which is just one slide, which just tells you that, okay, so we looked at a particular result, which is a model theoretic result in the context of the finite. And this gives a certain window into what kinds of things I'm looking at. So this is, these are the kinds of things that I'm looking at, that you're looking at classical model, basically just looking at classical model theoretic results. And you want to know, these results assume that the structures are finite and infinite. I mean, you have no constraint on the cardinality. But as you already saw, if you put a constraint on the cardinality, then things completely change. Watchtowers Theorem, a very elegant theorem from over infinite structures, fails in the context of finite structures, right? So the idea is to do such kind of investigation for various other classical model theoretic results and try and see what happens in the finite to these. Okay, this is also in the same spirit as amongst the earliest motivations for the development of finite model theory. Indeed, Petr Hayek in the mid-70s explicitly posed the question of developing a model theory for finite structures. Okay, it is a different fact that finite model theory developed because of its connections with computational complexity and databases. Okay, and most of these initial results, largely because the relational model was there by Cord, you had most of these results initially, a large part of the results of finite model theory as investigating database results, investigating database theory or computational complexity. Descriptive complexity is a branch of finite model theory which entirely studies this correspondence of the kind that Shubhashish asked. Yeah, complexity classes and their logical definitions. Database theory, well, finite model theory is regarded as the backbone of database theory. PODS is the standard conference for finite model theories. Okay, but these were historical developments. But the original program of developing model theory for finite structures was trying to look at these classical model theoretic results and trying to see what happens in the context of finite structures. Okay, so that particular program picked up in the mid-90s. Okay, largely by Gurevich. And then subsequently many works came, and in fact it even inspired the development of many graph classes that are now very are of much interest in algorithms and in structural graph theory. The homomorphism preservation theorem indeed led to the development of no-dense classes. Okay, that was the original motivation. So my research interest is largely in this original program, and to try and see what happens to these classical model theoretic results in the finite. If there is a failure, then you attempt recovery by doing one of two things. Either you generalize a logic fragment like we did from existential sentences to more general prefix classes. If first order logic itself fails, then go to higher logics. Okay, so that is one kind of development. Another is you look at first order logic, but you restrict your classes of structures. This particular program has turned out to be particularly fruitful, where you look at classes of structures that are algorithmically interesting. Look at classes of graphs that are bounded degree. Look at classes of graphs that are of bounded tree width, of bounded clique width. Okay, and now what happens to these kinds of model theoretic results when you know that there is structure which you can exploit? Okay, so indeed many such model theoretic results actually hold. So Watchtowers theorem holds over classes of graphs of bounded tree width. More generally, class of structures that are wide under some closure assumptions of hereditariness and additivity. Homomorphism preservation theorem was really the driver, which was an open problem for many years until it was solved by a master student before his PhD, but not an ordinary master student. But nevertheless, that led to a development of many graph classes. So these special graph classes have nice model theoretic properties, and these model theoretic properties actually serve to explain good algorithmic properties of these classes. So that's what really I'm looking at these model theoretic results and trying to understand the connection with algorithms and structural graph theory. As you already saw, Watchtowers theorem gives you a structural meta theorem. And you can show that another result called the Lowenheim-Skolem theorem really gives you algorithmic meta theorems. Okay, so those connections is something that I'm interested in. And I just conclude by saying that logic can provide a unifying perspective to understand a variety of structures and properties of interest in theoretical computer science. Posits, graphs, hypergraphs, relation structures, point configurations in the plane, geometric setting, you can all look at them uniformly from the point of view of logic, and you can analyze them. Likewise, properties like, triangle, whatever, vertex cover and so on, they're all expressible using first order logic with special kinds of properties. Once again, logic serves in the property realm as well, to be able to serve as a unifying perspective for many things in theoretical computer science. So that is my thing. I'll just conclude by saying Dhanyavad.
Thank you, Abhishek, for the talk. So I think we have some time for a couple of questions. And Paritosh, you have a question, please go ahead.
Hi, Abhishek.
Hi, Prasman.
So, interesting talk. When you said you are nearly done, I thought you were going to sing. Abhishek is a very good amateur singer.
Oh, God.
Okay, to the question. So you show that Tate sentence cannot be expressed in pi 3, right?
Yeah.
And Tate sentence essentially requires this power of data logs, sort of bottom-up inductive computation, something like transitive closure. Now,
Correct.
to detect gaps, intuition is that you need a transitive closure to find where the gaps are. So would this proof extend to show that it cannot be done in any pi k by suitably arranging gaps in, larger structure?
Definitely. I mean, the result shows that pi k will not, all these examples, sum total Rn, of course, I didn't get to spend much time on sum total Rn, but the intent was to show that sum total Rn, this generalized sentence, is expressible in Datalog, and it is expressible in Datalog for the very same reason that you can express reachability kind of things in sum total Rn, and it is not expressible in pi 2n plus 1 was this.
No.
So
Tate sentence, which is in sigma 3 intersection Datalog, cannot be done in any pi k for any k.
No, well, sigma, it is already in sigma 3, so therefore it is already in pi 4.
Oh, yeah, of course. Sorry, just being very stupid. Yeah. So you have to do that.
So that is why that result is, in a certain sense, optimal. It is in sigma 3 and not in pi 3. But if you go one step higher, then of course it is there in both of them, sigma or pi.
Right. Okay. My only other question was, what was the reason for this Rosen-Weinstein conjecture? Datalog and pi k.
I don't know. It just appears in their so the paper is titled some preservation theorems in model theory, finite model theory, and they are looking at their essential goal is they know the failure of Watchtowers theorem from Tate from 1959. Now they're trying to look at various, and this was a very important program in finite model theory to look at infinitary logics in the finite. Okay, so they started to look at infinitary logics and then trying to say, okay, what kinds of subfragments of infinitary logics can be utilized to be able to describe these extension preserved properties.
Okay.
So it is in this context that they ask various questions. Is it the case that FO intersect Datalog can be expressed using L infinity omega with something in the existential fragment of L infinity omega? Is it the case that you can so all of these kinds of results you had? So there are various languages that they have. They have Datalog, they have L infinity omega, they have finite variable logics, they have prefix classes now. And now they are trying to understand whether all of these failure results can be somehow recovered by changing the logic. Okay. Once you change the logic, you can ask various questions, because you can say first order intersect Datalog, is it inside some L infinity omega? If this is true, is it the case that L infinity omega intersect Datalog is inside L infinity omega, some existential fragment? Yeah. So this whole space of results where you consider different kinds of logics and you ask these recovery kinds of questions was the context of which one of these questions was prefix classes. That appears towards the very end of their paper. Is it where they say that can prefix classes serve to capture FO intersect Datalog with negation queries in the finite, be it not the lowest level? That was the way in which they phrased it. Yeah, be it not the lowest level, can prefix classes serve to capture this? Is a certain question that they ask, and then they conclude the paper with some general remarks. So this is the context within which they are operating. It's the context of recovering preservation theorems in the finite using different logics other than FO.
Okay. So when you answered that, this Tate sentence can be done in pi 4, it's pi 4 without Datalog, right?
It's just plain pi 4. It's already sigma 3.
It's in Sigma
Tate
3.
sentence.
Oh, yeah, of course. It's in Sigma 3 intersection data log. So it's already in.
So it's in Sigma 3
Yeah,
and therefore
yeah,
it's in
okay.
Tate.
Okay. So you don't need power of data log in order to do Tate sentence.
You do not need the power of Datalog. No, it is an extra observation that the sentence is constructed such that it becomes expressible in Datalog. It's an extra observation.
Okay, thank you.
It did not intend to Tate just gave it as a first order sentence, but
Yeah.
it was the observation of Rosen and Weinstein.
Okay. Okay.
Possibly, in fact, even going to even Gurevich and Chela, maybe in fact even Gurevich and Chela observed this because they themselves came up with an example for the failure of Watchtowers in the finite in 84, but they somehow claim it as an independent construction that they came up with. But they seem to have made this observation about Tate, and which Rosen and Weinstein quote and so.
Thank you. I'm done. Yeah.
So are there other questions? Okay. So if there are no other questions, then let's thank the speaker again.